Thanks for tuning into this Revision Zone Maths video. In this video, we will be calculating derivatives of polynomial type functions. In particular, we'll be calculating these derivatives without referring to the limit definition of a derivative. Let's begin with some examples. So we want to be able to differentiate the three functions we have here. They are all of the form x to the n, of course. And because we don't want to go back to using a limit definition, we're actually going to use a result which we proved in the first video, the video in part 1 of the series on differentiation, which was if you've got a function x to the n, then you can differentiate it directly and you will obtain nx to the n minus 1, where n is obviously a natural number. Right? So if you're not too sure why this is true, then please feel free to go back and take a look at that video. So using that statement in the red, I can basically differentiate the first function, and I'll simply get f prime x is 4x cubed. Now, statement 2, or question 2 in this example rather, I can't use the statement in red immediately. And obviously the reason for that is the power, in this case, happens to be -3, which is not a natural number. Now, the good news is, the statement in red, actually, even though we only showed it for n being the natural number, it's actually true for n being any real number, right? So I should write that here, perhaps. The proof is rather technical, so we need not really get into it, but the point is, I can differentiate this y equals x cubed function directly by using the statement in red again. So I'm going to get minus 3x to the minus 4, no less. And lastly, the function g of x equals x to the power 1.29. Since 1.29 is a real number, again, the same statement in red actually serves us rather well. And in this case, when I differentiate g, I get g prime. And the way I get the derivative is I multiply by the power, I write the x down, I subtract 1 on the power according to the rule, and I end up with 1.29 x to the power 0.29. So the second example, we have more functions, which are again polynomial type functions, and we will differentiate these quite directly. Again, we need to really just go back to the statement we had for the last example, which is a standard polynomial x to the n can be differentiated to give you an x to the n minus 1, where of course n is any real number. So using again the statement in red, I can differentiate the first function directly, but I need it in an appropriate form. So let's combine the powers using laws of indices. So I get x to the 5 here, and we can differentiate this to say f prime x is indeed 5x to the 4. Now, part 2 of this example, again, we've got a function, it's in a slightly messy form, we want to get it in the form x to the n, and we can again use laws of indices. In this case, because the things are being divided, we can subtract the powers, so we get x to the minus 2, and we differentiate this directly to just say the derivative is minus 2x to the minus 3. Now, this is where we can't use the statement in red immediately, because the function is looking somewhat different to the sort of functions we've had so far. However, we again showed in the video series for differentiation in part 1, of course, that if I've got a function of the form f of x is equal to a f of x, where of course the first f is a capital and the second f is a lowercase, where a is any real number, then if I want to differentiate the capital f of x, the a just comes along for the ride, and I really just have to differentiate the lowercase f of x, right? So a special case of this would be if I take my f of x to be x to the n, right? Then what do I have? My capital f of x becomes ax to the n, and therefore by the formula, which I should mark clearly because there are lots of formulas here, by this formula here, I can basically say the capital f of x differentiated, the a is going to come along for the ride, and I'm going to get nx to the n minus 1. Sometimes you'll see it written as na x to the n minus 1. So now using this statement in green, we can basically start to differentiate the last two functions we've got on this on the screen. So g to the x, when I differentiate this, the 6 just comes along for the ride, and I multiply by 5 over 4 x to the 5 over 4 minus 1, right? We can tidy this up a little bit to say, let's see, so how many 2's go into 4? Well, 2. How many 2's go into 6? Well, 3. So I'm going to get 3 times 5, which is 15 over 2 x to the quarter, right? So that's the derivative of g. And the derivative of y, which is the last part of this example, well, pi is a real number, so it's just going to come along for the ride. I'm just going to get 7 pi x to the 6. Let's look at the next example. So in this case, we have to differentiate 2y squared minus x cubed equals 0, and we're told y has to be positive. So again, we are going to reuse the statement that we actually had in the last example. Let's write it down in the sort of more general form. So if we've got f of x equals a x to the n, then the derivative is just going to be na x to the n minus 1, where a and n are any real numbers, right? So we want to get this expression. We want to get the expression of our function here in a suitable form to be able to use the statement in red. So let's try and do that. So solution, we've got 2y squared minus x cubed equals 0, where y is of course positive. So we're going to rearrange this to get y equals something explicitly in terms of x. So I can take the x cubed to the other side, and then I can divide through by 2 to get y squared is x cubed over 2. And of course, at this stage, I can take a square root, right? So if I write a square root as a power of a half, then this is where the fact that y is positive is important, because when we take a square root, it could be a positive square root or a negative square root. And of course, we're told that y is positive, so the square root must itself be a positive square root. So then we can write down y is actually x cubed to the half over 2 to the half. And simplifying this, it's 1 over root 2 x to the 3 over 2. And now this is perfectly in the form ax to the n. So I can differentiate this very directly. The 1 over root 2 comes along for the ride, and the x to the power 1.5 can be differentiated to give you 1.5 times by x to the power of 1.5 minus 1, which of course can be tidied up to say 3 over 2 root 2 x to the half, and we've worked out our derivative. Now it is worth making a comment here, and the comment is actually we know that derivatives carry geometric information about tangent lines to curves, and in this case our equation 2y squared minus x cubed equals 0, for y being positive of course, describes some curve, and dy by dx actually gives us information about the gradient of tangent lines. Tangent lines to our curve at the point xy. This was of course mentioned in part 1 of our video series on differentiation. Example 4 requires us to work out the equation of a tangent line. So it says find the tangent line to the curve 2y squared minus x cubed equals 0 at the point 2, 2. So let's get stuck in. So solution. Since we know this is the exact curve we dealt with in the last example, and we also mentioned as an afterthought after having calculated the derivative, that derivatives actually give us information about gradients of tangent lines, then we need not actually start with doing a lot of calculation here. We can just say we know that y equals x to the 3 over 2 over root 2, and then from last example we actually showed that the derivative of this is actually going to be 3 over 2 root 2 x to the half. So we know what the derivative is. We want to work out the value of the derivative at the point x equals 2. So the way we write that down is dy by dx, and we're going to evaluate this at x equals 2. So when I write that down, I'm going to replace my x in my formula here. I'm going to replace it with 2. So I'm gonna do that. And of course, this is 3 over 2 root 2 times by root 2, and the root 2s are going to cancel, and I'm going to end up with the derivative being 3 over 2. Now this tells me that the gradient of the tangent line to the curve 2y squared minus x cubed equals 0 at 2, 2 is actually 3 over 2. Now, with this information, we're in a position to be able to calculate the equation of the line, right? So let's work out the equation of tangent line. So how we're going to do this? Well, the tangent line is a line, so it's a straight line, so it must have form y equals mx plus c, where m equals gradient and c equals y-intercept, right? Which are both constants, of course, both constants. Well, we know what the gradient is. We know that the gradient is actually 3 over 2 because that's precisely what the derivative tells us. So we know m equals 3 over 2 and x equals 2 and y equals 2. We know these conditions are true, so we can basically substitute them into our general equation of a line. Let's make a bit of room. So we can substitute them into our general equation of the line. So we can say 2 is equal to 3 over 2 times by 2 plus c, right? Because just to be absolutely crystal clear, my y is 2 and my x is 2, and of course my gradient, which is what we spent the first part working, is 3 over 2. So we can completely solve this to say 2 is equal to, well, 3 over 2 times by 2 is just 3 plus c, which then tells me c is actually 2 minus 3, which is minus 1. So I now have a value for my gradient, which I knew from before, and my y-intercept. So I can write down the equation. Therefore, y equals 3 over 2x minus 1 is the equation of the tangent to our curve. At the point 2, 2, indeed. So in this case, we have functions that are polynomial type, but they're looking a bit more complicated. In particular, they have more than one term, right? So we've not quite seen how to do this. So let's have a think about this. What we did show in part 1 of our video series on differentiation, that if we have a function which is made by actually adding two functions up, then by definition of differentiation, it was shown that you can actually differentiate the overall function by differentiating each function and then adding them up, right? So we can completely use this result here to be able to differentiate each of our functions that we have. So let's have a look at the first one. So I'm going to write down the derivative, which is going to be dy by dx. Firstly, I'm going to differentiate the first function, which obviously is a standard. It's off the form that we've already seen. Just for the sake of convenience, I will write down here. So if we've got something like, say, y equals ax to the n, then we have already seen that the derivative is just going to be an x to the n minus 1. Sometimes people write it as na x to the n minus 1, which is of course exactly the same, where a and n are real numbers, of course. So we're going to use this result in blue to be able to differentiate the first one, which is going to give us 10x. And again, we're going to go back and differentiate the second one, which is going to give me 3 times minus 2, which is going to give me minus 6 x to the, if I subtract 1 from minus 2, I'll get minus 3. So the derivative actually turns out to be 10x minus 6x to the minus 3. Now let's look at part 2 of this example. Well, we're going to use the exact same idea as we used in part 1. The only thing perhaps that's worth saying is above we had 2 functions, but actually it doesn't really matter how many functions you have. As long as you have a finite number of functions, you can always just differentiate each term and get the result. In other words, what I'm trying to say is basically this result here can actually be extended to having more functions, right? We need not get into the technical details. Let's just figure out the derivative. So again, we're going to do one term at a time. So let's make sure we look at the first term. We differentiate that. Again, standard sort of thing. We multiply by the power. We subtract 1 on the power. Then we differentiate the second term. That's again a standard polynomial type thing. So we multiply by the power and we subtract 1 on the power. And last but not the least, we differentiate this. Now, that can be thought of as 4 times x to the 0. So we multiply by the power and we subtract 1 on the power to get minus 1. And of course, this can be tidied up. So 6 times by 3 over 2, I can cancel things to say 9x to the half. And then the other one could be x to the minus a half. And finally, the last term would just be 0, which can just be written as 9x to the half plus x to the minus a half. So moving on to the next example, we see that we have to differentiate an order 4 polynomial. So let's just jump into this. So the solution, we can obviously, from the results we've seen in the earlier example, we know that we just differentiate each term at a time, and each term can be differentiated fairly directly without having to go back to the definition of a derivative. So let's be systematic about this. So the first term we differentiate is x to the 4. Well, we use, as always, the statement that if, I shouldn't say f here because f's already been used as a symbol. Let's say y. So we know that if I've got something of the form ax to the n, then the derivative is basically an x to the n minus 1, where a and n can be any real numbers, right? I'm just writing this down again because as long as that idea is clear in one's mind, you know, this thing can be very, very easily done. So the first one differentiates to give me 4x cubed. And then the second part, the second term differentiates to give me, well, 3 times 3 is 9. So it's going to be 9x squared. The third part, well, I've got minus 9 times 2, which is minus 18. And when I differentiate, so sorry, the 2 is going to be, we're going to have to subtract 1. So I'm just going to get x to the power 1. The next term is just 24x, but of course 24x is 24x to the 1 because the power there is 1. So I just get 24. And last but not the least, minus 20 can be thought of as minus 20x to the 0. And using this rule here, I basically would just get 0. So it would be minus 20 times 0 times by x to the minus 1. But of course, this whole thing is just going to give me 0. So the derivative actually is 4x cubed plus 9x squared minus 18x plus 24. So the reason why I chose this example was because of 2 reasons, really. I wanted to highlight that generally, when we differentiate a polynomial of order n, we get a polynomial of order n minus 1, i.e. differentiating reduces the order, differentiating reduces the order of polynomials by 1. This is good to know because it's a useful check. So in an exam situation, or if you're just doing a homework problem and you differentiate something and you can clearly see that the order hasn't gone down by 1 overall, then you know you've made a mistake. The other thing which is worth mentioning, I will actually say it here. So generally, and this is a general statement, every constant function differentiates to 0. What do I mean by that? So if I have something of the form y equals c, right, then what I'm saying is the derivative is actually, with respect to x, it's just going to be 0, right? Where c is some constant number, where I should say where c is some real constant, right? And of course, we've seen this already because we've seen it here. The 20 actually goes to 0 when you differentiate it, right? Yeah, so with that, this example comes to an end. So let's look at the next example. We're now getting closer to the sort of things we're likely to see on exam papers and so on. So let's differentiate this. We've got 2 functions. Let's start with the first one. To be able to differentiate this, we are just going to be using the ideas we've already seen. I won't bore you with all the details. What I will do is I'll say, well, to be able to differentiate this, I better expand this because I don't know of a way of differentiating when 2 functions are being multiplied, right? So far, I've got a function here, and then I've got another function here, and the 2 are being multiplied, and I can't quite handle that with my current knowledge of derivatives. So let's expand this. So when I expand this, I get x cubed minus x squared plus 2x, and now this is looking a lot nicer. So now I've got something where I've got 3 different functions, but they're actually just being added. So I've got the first one there, the second one there, and the third one there, right? So let's differentiate each function term by term, and I can write down what the derivative is. So the first one gives me 3x squared. The second one gives me minus 2x, of course, because there's a minus out here in the front. Should perhaps tidy this up. And then the last one, the 2x, differentiates to just give me 2. Good. So let's look at the part 2 of this example. And again, we've got a similar sort of issue with this problem here, which is, so far I've got a function on top and I've got a function at the bottom, and I don't really know how to handle things like that, right? So I'm going to have to somehow express this in a form where I've got functions that are actually added up. Similarly, I've got a function here, and I've got another function here, right? So I'm going to have to re-express them in a way much like I did in part 1 of this example. So let's tidy this up. We're just going to use some basic algebra to collect terms. So I'm going to take that fraction and split it up into 2 fractions. And I'm going to expand this by expanding the bracket. So I'm going to get 3x to the 4 plus x cubed. And now I need to tidy up these fractions to get them in the form x to the n. So I'm dividing things with the same base, so I can just subtract the powers. 3 minus a half is 2.5, which is of course 5 over 2. And x divided by x to the half is just also x to the half. So now my function is looking so much nicer. The function now is very clearly just lots of individual functions that are actually summed up, and we know how to differentiate this. So we can just differentiate each term at a time. So the first term, the 2 just comes along for the ride, and the x to the 5 over 2 gives me 5 over 2x to the 3 over 2. And then the 3 just comes along for the ride. For the second term, I'm just going to have a half x to the minus a half. And then 3x to the 4 differentiates to give me 3 times 4x cubed and x cubed differentiates to give me 3x squared. Now, all that's left to do is to tidy this up. So we go back to the first term here, and we say, well, the 2's are going to cancel. So I'm just going to get 5x to the 3 over 2. And the 3 over, for the second term, I'm going to get 3 over 2x to the minus a half. And then for the third term, we're going to get 12x cubed, and finally 3x squared. So we've been able to work out the derivative of both those functions. Of course, as you saw, the key idea there is to be able to re-express all of the things you've got, each term, in the form ax to the n, right? And as long as you've got lots of terms of those forms, whether they're being added or subtracted, you can differentiate each term systematically at a time and work out the answer to the overall thing. So example 8. This example requires us to essentially work out the equation of a tangent line to a cubic that we've been given. Of course, we've done an example similar to this earlier. However, the difference here is the function is somewhat more complicated than the one we've seen before. So let's solve this. Let's just do what the question asks us to do, which is to differentiate the curve to find the gradient at the point minus 1, 2. So my curve is y equals x cubed minus 3x plus 2, and we just differentiate this, right? We differentiate each term at a time. So the first term differentiates to give me 3x squared, the second term gives me minus 3, and because 2 is a constant, then it's just going to be 0. But of course, I can just rewrite that as minus 3x squared minus 3. Now, we can evaluate the derivative at the point x equals minus 1. So we go back to our formula of a derivative and we replace x by minus 1. So it's going to be 3 times by minus 1 squared minus 3, which is actually going to give me 3 times by 1 minus 3, which is going to give me 3 minus 3, which is 0. Now, this is fantastic. So this makes our life really, really easy. So the second part says use it to work out the equation of a tangent line. Now, given that the gradient is 0, so gradient is 0 is 0 for our tangent line, right? That tells us that our general equation of the curve, so equation of the tangent, so equation of tangent, it's got to be of the form y equals mx plus c, right? Where m and c are real constants, with m being the gradient and c being the y-intercept. So since our gradient is actually 0, we know that m equals 0, and we also know that the point 1 minus 2, or minus 1, 2 rather, actually is where we're interested. So what we can basically say is x is minus 1 and y is 2. So with that, we can use that to work out what c is. So we can say, well, y is 2, m is 0, x is minus 1, and c is what we're looking for. So we've literally substituted the values of x, y, m into this general equation here. And we solve for c. So we say c equals 2. Therefore, y equals mx plus c becomes y equals 0 times x plus 2, which of course is just the same thing as y equals 2. And this is the equation of our tangent line to our curve in this case. So example 9 is a little bit different in flavor. We're given a function and we're told that when you differentiate the function and evaluate it at x equals 2, the value of the derivative is actually 3. And then we have to find out p, where p is an unknown in the function that we've been given already. So let's solve this. So we write down our function. Well, of course, it's 12 over p, x to the minus a half plus x. That's our function. And we're told that x has to be positive, right? It has to be positive, of course, because we're taking the square root of x, and negative square roots are going to cause problems. So given that the question tells us that the derivative of f at x equals 2 is 3, we're going to basically use that statement. So we're going to differentiate f. So let's differentiate this. Again, this is a standard sort of thing. The 12 over p just comes off the right. I multiply by the power and I subtract 1 on the power to give me minus 3 over 2. And the derivative of x is obviously x is x to the 1. I just do 1x to the 1 minus 1, which the whole thing simplifies to give me minus 6 over p, x to the minus 3 over 2 plus 1 times by x to the 0, which of course is just minus 6 over p, x to the minus 3 over 2 plus 1, right? So that's my derivative. Now I evaluate the derivative at x equals 2. So I've substituted sub x equals 2 into derivative, right? We were, in the Leibniz notation, we were writing this like this. We would say divide by dx, and then we would say x equals 2, right? But obviously here we're working with a Newtonian notation, so we would write it as follows. So when I do that, I'm going to get minus 6 over p, and then x is 2 to the minus 3 over 2, and then plus 1, right? So let's tidy this up a little bit. So I'm going to get minus 6 over p, and then the negative power means it's 1 over 2 to the 3 over 2, and obviously the whole thing is being added 1. And then tidying that up a little bit more, well, it's just going to be root 2 cubed by rules of indices. And yeah, I can simplify that a little bit because root 2 cubed is going to be, p obviously is going to come along for the ride. It's just going to be 2 times by root 2, right? And we can now simplify a little bit to say, well, there's 1, 2 there, and there's 3 of them there. So really what we have is we have negative 3 over p root 2 plus 1. And since we're told that actually when I do this derivative and evaluate it at 2, the answer should be 3, I can then say I should have minus 3 over p root 2 plus 1 should actually be 3. But now I can use this to be able to work out what the value of p has to be, right? So I keep this on the left hand side. I take 1 away to get 2. I multiply through by, say, negative 1, so I get 3 over p root 2 is equal to negative 2. So then we can say 3 is actually equal to negative 2 times by p root 2, okay? So let's just make sure that's sectioned off so it's not interfering with our working here. So let's divide both sides by negative 2, so I get 3 over, or even negative 2 root 2, right? That's going to be our value of p, because obviously here we've got negative 2 root 2p is actually equal to 3. So the two statements, these two statements are completely identical. So we can use the second statement and actually get to our result in a much more neater way. So we've been able to work out the value of p. So our last example is again going to get us to use differentiation, but now to do something a little bit more interesting. In this case, we're given a curve x cubed plus 3x squared plus x plus 5, and we're told to find out the points, or rather the x value even, where the gradient of the tangent lines are going to equal 1. So let's work out a solution. Since we're dealing with gradients, right, then we know that we have to differentiate our curve to be able to work out the gradient. So we basically say our curve is x cubed plus 3x squared plus x plus 5, and we can differentiate it to say, well, we differentiate each term as we've been doing so far. It's going to give me 3x squared plus 3 times 2 is 6, and then that's 6x, and x to the power 1, so I'm just going to get 1 there, and a constant term differentiates to give us 0. We saw that earlier, right? So my derivative actually happens to be 3x squared plus 6x plus 1. So the gradient of tangent tangents to curve is given by the function 3x squared plus 6x plus 1. Since gradient equals 1 is the special condition that we're working with, must be true, then we've got 3x squared plus 6x plus 1 equals 1 must be true. And then we now just solve this for x. So we subtract 1 on both sides to get 3x squared plus 6x equals 0. This is a standard quadratic, and we need not go to the formula of completing the square here. We can just factorize the x out, and we can say 3x plus 6 equals 0. But of course, if two numbers are going to multiply to give me 0, and the two numbers are here, of course, that's the first one, and that's the second one. So if two numbers are going to multiply to give me 0, at least one of them has to be 0. So either x equals 0 or 3x plus 6 equals 0. But of course, if x is 0, that's fine. We've got a value for x. But if 3x plus 6 is 0, then we have to solve this. So we solve this to say 3x has to be minus 6, and x has to be minus 6 divided by 3, which of course is minus 2. So either x is 0 or x is minus 2. Now, since we actually want points, so let's make that very clear. We want the coordinate of points, right? The x value alone is not good enough, but it is good enough to at least help us work out the coordinate. So we know that y equals x cubed plus 3x squared plus x plus 5 is the case. Since that's the case, I can say when x equals 0, I can put 0 into that cubic, I get y equals 5. So one of my points is 0, 5. And similarly, I can say when x equals minus 2, I can put the minus 2 into the cubic, and we can work out some y value, right? Which it's not the most interesting thing necessarily to work out here, so I'll just leave that. To end, what I would say is we hope you found this video useful and want to see more, of course. Do use the comment section to say which topics you would like to see more videos on, and hit the like and subscribe buttons. We will see you in the next video.